Next up for gases are the idea of mixtures of gases. This becomes extremely important in several applications of chemistry. So we'll go through about three particular types of problems that you'll see, and then hopefully you'll see some others along the way. So this is based on John Dalton's law of partial pressures, and according to that law, according to John Dalton, the total pressure of a mixture of gases equals the sum of the partial pressures that each gas would exert if it were present in the container alone by itself. In other words, the total pressure within a container would be equal to the sum of the pressures of each individual gas. So however many gases are present inside that container. Now, the most obvious application of this would be in a situation such as this, where you have two containers, gas X in the container on the left, gas Y in the container on the right, and if we open up the valve, what would be the total pressure inside of the containers? So our first instinct would be, oh, well, pressure total would equal pressure of gas X plus pressure of gas Y. Pressure of gas X is 3 atmospheres. Pressure of gas Y, 2 atmospheres. And so we would get a total pressure of 5 atmospheres. And that would be absolutely incorrect. Remember, the law, Dalton's law, specifically states that it's the pressure that each gas would exert if it were by itself in that container. Well, when we open up the valve at A, if we imagine that Y is not present, then gas X is going to spread out in both parts of the container. So if I look at the pressure of gas X, okay, well, pressure of gas X initially and the volume of gas X initially have to be equal to the pressure of gas X at the end times the volume of gas X at the end. All right, so this is just Boyle's law, where P1V1 equals P2V2, and if we solve for the final pressure of gas X, we would have initial pressure times initial volume divided by the final volume. Plug those in. We have 3 atmospheres, initial volume of 4 volumes, whatever units they happen to be. Final volume would be 10 total volumes. So we would get a final pressure for the gas X of 1.2 atmospheres. Similarly, if you did a calculation for the pressure of gas Y, you would get a final pressure of also 1.2 atmospheres. Now we can go ahead and do the pressure total would equal the pressure of gas X final plus the pressure of gas Y final, 1.2 atmospheres plus 1.2 atmospheres gives us a final pressure of 2.4 atmospheres. All right. So combining volumes of gases is one important application of gas mixtures. And again, you want to avoid that quick and easy, just add the two pressures together. You have to consider the fact that when the two gases mix, both gases are going to occupy a larger volume than they started with. So this apparatus should look somewhat familiar. We did this last year. For those of you who are in honors chemistry, we did the molar volume of hydrogen gas, in which we had a piece of magnesium down in the bottom of a eudiometer tube that was wrapped in a copper wire cage. Above that was a solution of hydrochloric acid. So as the hydrochloric acid came down, it reacted with the magnesium ribbon, produced hydrogen gas. So up in our eudiometer tube, we had hydrogen gas being produced from the reaction, forcing the water down. But what we also had inside there, in addition to the hydrogen gas, was water vapor. So in our calculations, we had to take that into account, that above this, above the water, above the liquid water would be water vapor that would mix in with the gas. So in our calculations to determine the volume of the hydrogen gas produced, or any calculation that we had to do with that, we had to take that into consideration. So we'll take a look at that in the next problem. But oftentimes, if we're generating a gas, we're going to collect that gas by water displacement, similar to this and what we see in the next problem. So here's a typical problem where we're collecting the gas by water displacement. And we'll just take a minute to write down the equation for this reaction. So we've got hydrochloric acid reacting with calcium carbonate in the bottom of the flask here to produce carbon dioxide gas, liquid water, and aqueous calcium chloride. Now, being kind of systematic in our work here, we're told that we have an excess of the hydrochloric acid, similar to what we had last year when we did the reaction with magnesium. The calcium carbonate, we have 20.0 grams of the calcium carbonate, and the volume of gas in the tube that's produced here, right, so the volume in here is 87 milliliters. We know that the temperature is 25 degrees Celsius, or 298 Kelvin. And we're also told that the vapor pressure at this temperature is here. So that gives us the pressure of the water that will be inside that container there. And it wants us to determine the total pressure inside the tube there. Obviously, our total pressure inside the tube is going to be equal to the pressure of the carbon dioxide that's produced plus the vapor pressure of the water. Now, we already had the vapor pressure of the water, so we're going to be able to plug that in. How do we get the pressure of the carbon dioxide? Okay. Well, we go ahead and bring in our PV equals nRT. And so we'd have the pressure of the CO2 would equal moles of CO2, R, our universal gas constant, our temperature, divided by the volume of the CO2. So we need to get the number of moles of CO2. We know R, we're given T, and the volume of the container. Now, you might be tempted to think that that 87 milliliters that's in there is the volume of both of them combined. Well, it is, but remember, the carbon dioxide is going to fill that entire space up. It's not going to really even know that the water's there, the water vapor is there. So all we need to do is figure out the moles of carbon dioxide produced. So we have a little stoichiometry to do to get there. So we have 20.0 grams of our calcium carbonate. We have 100, if I did my math right, 100 grams of calcium carbonate to 1 mole of calcium carbonate. And for every 1 mole of calcium carbonate, we have 1 mole of CO2. So we'd have to go through and balance the equation out, but I think you see that if we do balance the equation to there, and everything else balances out correctly. Right. So this is going to give us the moles of CO2. So we can go ahead and continue on with our problem over here. Let me just do kind of clear some space here for us. So moles of CO2 ends up being 0.200 moles. R 0.08206. Again, is liter atmospheres over K moles. So we've got to squeeze the temperature in there. So temperature, remember, was 298 Kelvin. We'll squeeze that right in there. All divided by our... Now here's the final type of problem that we'll discuss here, where we have two different gases combined in a container, and we want to figure out the partial pressure of one of the gases if we know the partial pressure of the other gas. All right, so what we're going to do here is we're going to make use of use the ideal gas law for both of these gases, and basically use a little bit of mathematical manipulation of the algebra to help us out. So if I were to look at, let's put the pressure. All right, we'll put the pressure of the unknown gas on the top, which is the nitrogen, and we were going to compare that to the pressure of the O2 gas on the bottom. All right. If I rearrange PV equals nRT to solve for pressure, I would get number of moles of nitrogen, RT over V. So that would be for the pressure of nitrogen equals nRT over V. And same thing for the oxygen, only I would get the moles of oxygen, RT over V. And what happens here is that the RT and the V end up canceling out. They're in the same container, so they're going to have the same volume, the same temperature, and R is the same for both. So what we find out is that the ratio of pressures of the nitrogen and oxygen is the same as the ratio of the moles. So we can actually go through and figure out the number of moles given the masses of each gas. So doing a little bit of math here, my moles of N2 is 1.5 moles. My moles of O2, 1.0 moles. So if I take a look at my pressure of N2, then it would be equal to the pressure of the O2 times the moles of N2 divided by the moles of O2. So 1.0 moles of the O2 times the ratio here, 1.5 moles over 1.0 moles, and we get 1.5 atmospheres. I believe we atmospheres for the pressure of the N2. Right. Now, if we extend this a little bit, just taking a moment here, if we're comparing the pressure of one gas, so pressure of gas A, to the pressure total, what we would have is the moles of gas A, RT over V, divided by the moles total, RT over V. And again, we cancel out our RT over V, and the top and the bottom as being the same. And we get a new relationship that tells us that the pressure of any gas in a mixture is equal to the number of moles of that gas divided by the total number of moles times the total pressure. All right, and then this part right here has a special value. It's given the symbol X sub A, and that's equal to the mole fraction. Okay. So oftentimes in a problem you'll be able to figure out that mole fraction, the ratio of moles of one gas over the total moles times the total pressure, and allowing you then to figure out the pressure of some individual gas. So we'll be using that quite a bit in problems as well. All right, so sorry about the length for this one and the mix-up on that one, but we'll definitely do some practice problems with this in class.